Thank you everyone. Thank you Elias for the introduction. So I think the first thing I want to correct Elias is that this is a team effort. So it's a good work done by us. Us is a team of students, staff, postgraduate staff. One of them seems to be sitting there. Ben, he's one of our valued members, team members here. And also there's BlueSat team involved. So it's a big project. We involve a lot of students in this project. So usually when I give the presentation, I get questions after the presentation that ask, oh, is this project going to be funded? Or is it going to actually be launched? So today, right after the launch, giving this presentation makes me feel vindicated. I don't have to answer that sort of questions anymore. I'm going to briefly run through what our CubeSat consists of. Practically a crash course on how to build a CubeSat, but I'm trying to reduce that down to a bit, to about just 10 minutes, hopefully. Let me know the time if that's too short or too long. PP1, so that's a primary payload 1. So first I'll go through the objective. The mission is to satisfy the requirements of the payload. Our primary payload, which is the ion neutron mass spectrometer, what happens is it flies in the lower thermosphere of the Earth, and it will sample these ions and neutron masses and measure them on the spot. And the data will be collected from these instruments, and we are responsible for collecting them and downlinking them and passing them to BKI. So that's our primary objective. But also, we would have other payloads on board. So there will be a GPS payload. So as I go through these slides, pay attention to the top right corner where I should actually try to emphasize what is actually designed and built by us at UNSW Sydney. And I'd like to go through first out of three. So the first one is the GPS payload. Amy will talk more about this. It's fully designed and built at UNSW Sydney. We have the hardware built here, we have the antennas built here, and we have the software built here as well. That allows us to have a lot of flexibility, a lot of capability, and potential for experimentation that can help our research students in doing GPS-related research in space. So secondary payload 2 would be Rush. Edis, which is my colleague, he will talk more about this later. It's mainly to do with robust electronics in space. And secondary payload 3, which is Cell 4, it's to do with proving a reliable kernel, which is a software that can work well in space under the harsh environments of radiation. So, so those are all things that we designed and built at UNSW. Now we have also the attitude termination. So to satisfy the conditions of the payload, which is the main payload where it's the ion neutron mass spectrometer, we need to point in a certain direction. To satisfy that, we need to be able to orientate the spacecraft. And to do that, we have an attitude sensor called CubeSense, and we have an actuator called IMTQ. It's actually a lot more complicated. I don't want to go through that process of understanding how the thing works, but essentially we have the control bit and then we have the estimation bit. And once you tie them up together, you can be able to point to the right direction. And although these hardware are bought off the shelf, we designed the algorithms, we tested them, we implemented them, and we verified that it works. So you take those boards that I put out just now, put them in a layout like this, punch them in together, and there you go, that's a CubeSat. Well, it's actually a lot more complicated than that. It takes a lot of effort to do that. If you've noticed, one of the challenges that we have is how minuscule everything is and how jam-packed we have in the design, such that there's hardly any space for wires to go through. There's hardly any space for additional electronics to sit in there. So that has been the main challenge, essentially, in this entire project. And if you look at on the side there, you can see the GPS antennas as well. So on top of having to have solar panels on the exterior, which I didn't actually illustrate here, we also need to have GPS antennas to support our GPS experiments, and also to provide accurate navigation on board. So having to be able to do that, that's a challenge as well. And also one thing that I left out as a payload, in fact, is the structure. The structure itself is a payload. It itself is an experiment to test how 3D materials can actually be used to produce CubeSats. And we have verified that it works. I'll show more results of those verifications later. So all of this that we're doing, although the aim is to do science, but it's actually part of a broader aim. And the broader aim is to actually foster and build the skills and experience in UNSW Australia to be actually able to produce CubeSats. And I think we've done that with the launch today. So a lot of other stuff that to build on that experience, a lot of other stuff has to be done. So after you put together that CubeSat in hardware, you also need to put together the software that runs in it. So you have the bus communications, how individual modules can talk to each other, and we designed the bus communications in such a way that if one item fails, the other two items that are still functional can actually talk to each other still using the bus. So we have to design power management protocols. We have to devise a development environment such that it's easy for volunteers who are working on a software to actually externally access the hardware and develop the software at home. So we use Git repositories, we use Atlassian Bitbuckets, we use a very agile methodology of developing the project, and we also used a very sort of modular system to control the CubeSat using what we call an interface box, where if you plug the interface box as a computer, you can control all the switches necessary to turn on and off the satellite, reset it as many times as you want, so you can test the software. And this whole development environment, that is also developed here at UNSW. So we've made it very easy for students to join in and want to work on small little segments of the project and then leave, right? So after all that is done, software is ready, hardware is ready, it's fully assembled. We have to go through environmental testing. And the environmental testing requirements are really harsh. This is dictated by what NanoRex want us to, the launch provider. So the assembly process is actually very tedious and difficult. Because of these harsh requirements. So I'm gonna just go through this. So thermal vacuum test is one of the main ones that we have to pass. So our structure actually, although it was 3D printed, it actually passed thermal vacuum test requirements. And also we have to go through vibration test. So to do the vibration test, we have to take our CubeSat, which is on top left corner, put it into this box, metal box, which I think we should talk a lot more later. And once it's sealed up, that's Mike there inspecting the rig and instrumentizing it, and that's where we actually will vibrate our CubeSat. And if I play this here, this is how harsh the tests are that our CubeSat will need to be able to survive. So it's 10.8 Gs of acceleration that we have to pass, and we passed all that. So let me go through back to how we got here. So we are at the stage where we're launched now, but the beginning of the project went all the way back to March 2012, where Elias was the one who initiated, and Andrew who initiated the project where expression of interest started. We were shortlisted, and we went through preliminary design review, which is March 2013. But then, between critical design review and flight readiness review is when we actually have a CubeSat that is fully tested and ready to go. But between that and preliminary design review, there has been a lot of changes. We've changed from one type of deployer to another type of deployer. We changed from one launcher to another launcher. The specifications changed. the orbits change, so the power modeling has to change. It's all these changes that make building this CubeSat so difficult. And the changes in the timeline, that means that your manpower change, people come, they work on it, and then they leave. The transitions, all these things you have to be able to handle, and that's what makes this project so difficult and challenging. And on top of that, we have a very limited resources. So this is all the funding that we've got to build the flight model on the top. We have, if you've realized, there's no government funding in this slide. Engineering model is one that we've got towards the end of the end of the project, where we only got that secured that funding after we delivered our CubeSat. So this amount of funding, we've managed to come this far. I personally think it's a testament to how much we can achieve with very limited resource. And if we are given more, we will be able to achieve more. So this project would not have been possible without all these team members and the BlueSat team and a lot of other team members who have joined previous to my involvement that had made it possible. There's a lot of documentation involved, and it's an honor to be in the team with such talented people to make this a success. So I am the team lead. I'm an engineering team lead. I guess that's the right word to use for this team, and I'm very grateful for the help of all these students, and it's important to acknowledge their contribution. So what to look for after this? So launch is today. The deployment will happen. I should correct this. The deployment should happen 15th of May 2017, and that will be for iInspire 2. The deployment of our UNSW CubeSat will happen a week after that, within a week. So things are very fluid at the moment. We will hear more from BKI about what they say about our deployments. So fingers crossed, we'll be able to get the signal once everything once it's deployed, and we'll hope for the best. So, all right, thank you everyone for your attention. Any questions? Sorry.
So I noticed that going upon the ISS deployment, it would have gone on in a NanoRacks deployer or the ISIS.
It's a NanoRacks supplier.
But you did your environmental testing on that ISIS deployer?
So we are following the NanoRacks requirement for the environmental testing, but it was, I think Mike can correct me if I'm wrong, Mike.
Yeah, we started the testing with the ISIS test pod, but there was an issue with that. There was a very high resonant peak around 500 hertz. So we abandoned the test and we moved on to the Cal Poly test pod. And the rest of the tests were completed in Cal Poly test pod, which is similar to the NanoRacks.
But it's being launched from a NanoRacks deployer?
Yes, correct. Okay. It will be launching from a 6U NanoRacks deployer.
So you put 3 of them in one deployer?
Yes.
Nice.
Joon alluded to the difficulties. You know, we've had over the years so many changes from DKI's side, launch, spec, you name it. So it's been constant sort of, you know, trying to figure out where we're going. So even now, he talks about the deployment. It was supposed to be 1 month after launch we have the first lot, a month after launch we have the second lot. We don't know yet.
Yeah. So if you go back to this slide back here, the launch date was supposed to be 2015 April. That was the initial plan. Got dragged out for 2 years and makes it really difficult for everyone. Any other questions? No.
I think it, okay.
Maybe one more. Sorry.
Is there any testing performed on the ISS pre-deployment, or is this just an anxious wait until it's deployed and you hope to get a signal once it's in orbit?
So what sort of tests are you talking
No,
about?
there isn't. It's essentially the ISS. What they do is they load them into the deployer and push them out.
Okay.
effectively, once we've delivered our satellite, it went to ISIS, they sealed it in the deployer, and that's it.
Thanks, Joon.
Thank you.